This course starts with a classic project design question. What is the best material for making a specific product? To best address this kind of question, we'll show you an optimized strategy aligned with the various stages of the project, but with a specific focus on the material. So let's start with a few simple definitions. A product is an object made by humans, either by hand or with machines, to serve a specific purpose. A material, on the other hand, is a natural or artificial substance used to make components or structures. To conceive, design, and create a product means turning an idea into something tangible. The choice of material is a crucial design aspect, as it allows you to optimize the product in terms of performance, cost, and manufacturing processes. However, choosing the right material is not a simple task. There are over 100,000 materials available, and the decision can depend on many factors, such as the geometry of the product, the budget, the requirements the product must meet, and sometimes innovative goals you want to achieve. Selection is generally based on the properties of the material, such as its mechanical properties, physical properties, or other factors which allow us to narrow down the pool of possible materials and to evaluate them. We can also quantitatively assess the performance that a specific material is able to guarantee. Given the large number of materials and the complexities involved in innovative design, it is necessary to use a structured, rational method based on data and calculation tools. And this is precisely the goal of the course, to provide a rational and systematic approach to material selection. The method we will illustrate is the one developed by Professor Michael Ashby, and it is covered in his textbooks, which will guide us throughout the course. To understand the pragmatic spirit behind Professor Ashby's approach, here's a quote. "Materials are the ingredients of engineering design. Choosing them well is the key to successful products." His internationally recognized textbooks are recommended as essential reading for anyone who wants to delve deeper into the concepts we will develop in this course, and to apply them in specific design contexts, such as mechanical engineering, industrial design, or sustainability. If well chosen and used creatively, materials not only improve a product's performance, but can transform people's lives, leading to real technological leaps. Materials have always marked the progress of humanity. It's no coincidence that entire eras are named after the materials that define them. The Stone Age, the Bronze Age, the Iron Age. For centuries, metals have driven technological development. Even in the 1960s, talking about engineering materials basically meant talking almost exclusively about metals. Then came the revolution of plastics, composite materials, advanced ceramics, and special alloys. Today, to quote Professor Ashby again, we no longer live in the age of a single material, but in the age of all materials. And looking at the cutting edge of innovation, we're in the era of advanced, smart, sustainable, and customizable materials. From nanostructured materials to eco-friendly ones, from biocomposites to metamaterials, everything is constantly evolving. On this topic, Mark Majadovnik, a materials scientist and one of the most famous science communicators, writes, "Materials shape the history of humanity. They define how we live, what we wear, how we eat, and how we build objects. They're not just passive matter, they're agents of change." Let's take, for example, a tennis racket. At first, it was made of wood. Solid, ash or maple, heavy, with a smaller head, it required more strength and skill. After the 1950s, aluminium and steel arrived, lighter, stronger, more dynamic. But the real breakthrough came after the 1970s with carbon fibers, light, stiff, strong. They changed everything. Rackets became more powerful, precise, and easy to handle. Graphite frames with foam cores also added comfort and shock absorption. And today, innovation never stops. Integrated sensors to analyze shots, eco-friendly materials, 3D printed frames custom-made for each athlete. Even the strings have evolved. From natural gut, we've moved to high-performance synthetic materials like polyester and nylon, often combined with systems to reduce vibrations and increase comfort. Materials are much more than just raw matter. They play a central role in making an object functional, reliable, affordable, but also beautiful, enjoyable to use, and sometimes even imbued with emotion. Having access to so many different materials first and foremost means design freedom. It means finding better, lighter, more effective, and more affordable solutions and sometimes it allows you to revolutionize a product, creating something that was previously unimaginable. Of course, when choosing a material, functionality is the most important aspect. A good technical design ensures that a product works properly, is durable, safe, and cost-effective. When the main focus of a project is technical, the approach to material selection is generally systematic. But a material can also be given an aesthetic, expressive, or symbolic value. Think about the use of steel or glass in contemporary architecture or plastics. Versatile, lightweight, colorful, capable of offering unique textures and surprising shapes. In this case, the design directions can head in very different directions from one another. And it is the designer's job to ensure that the choice of material remains true to the project's objectives. In recent years, the reasons behind material selection have become even more diverse. It's no longer just about finding lighter and stronger materials, but about seeking solutions that offer economic, functional, and above all, sustainable advantages. This transformation stems from two main factors. On one hand, technological and scientific advances, and on the other, global challenges and regulations. From an economic competitiveness standpoint, material selection is a balance between performance and cost, which varies depending on the sector. When cost is a critical factor, the focus in design is on saving. If, on the other hand, cost matters less, the goal becomes maximizing performance. In low-cost, mass-production sectors, the focus is mainly on optimizing already well-known materials. In high-value sectors, on the other hand, there is a greater openness to innovation, though never at the expense of reliability. Current regulations also push towards safer and more reliable products, while at the same time, there is growing awareness of the need for more eco-friendly and low-impact solutions. Given such a wide range of design approaches and materials available, there are countless possible solutions. And while some will be better than others, we move beyond the idea of a single possible scenario. That's why the first tool for a project designer is to have an open mind, to be able to explore all possibilities, and to know how to distinguish what is good from what is truly excellent. This brings us to the end of our brief introduction, in which we've seen that choosing the right material is essential for creating functional objects and successful products. The continuous evolution of materials transforms the characteristics of products. Design criteria, and therefore material selection, can differ greatly from one another, ranging from the classic considerations of functionality and cost to more recent focuses on sustainability and innovation. Designing is to turn an idea into a tangible product. Choosing the right material is essential to ensure optimal performance, cost-effectiveness, and efficient manufacturing processes. To do this, however, you need a structured method because there are thousands of materials and many variables to consider. That's what we'll try to develop in this course.